Okay, this is the first of perhaps several demonstrations of Module 3, and I'm going to start my timer, but actually I don't think I need to. It's 8:19:30. I'm going to start now. All right, so this is a demonstration of the GLM, both the MRC side of the GLM as well as ANOVA, and you'll see that I have prepared some slides ahead of time. I have data. This is the first 10 rows, and unfortunately it clipped off some of the variables, but there is a factor 8. So I have dependent variables, these y's. I have some covariates, 7 covariates, and I have 8 factors. The general linear model takes the form of both MRC and ANOVA. That means that it's pretty flexible. It's linear or additive, and that it's a model, and the model is specified as a dependent variable that is predicted or conditioned on a vector of weights assigned to a set of predictors. This X here is oftentimes referred to as a multiple predictors rather than just single, but that's what makes it flexible. And then finally, this epsilon is the residual of our model. So what we're expecting is that we can make predictions about y based upon some other conditioning, covariates for MRC and factors for ANOVA. So what do we assume? We assume the Gauss-Markov assumptions that I'll talk about at length during the discussion. And I'm going to demonstrate all of the results with my models. So you'll notice that I've also included the code, the R code, just for people who might be interested in this. I ran my first MRC model using Y4, and I used X1 and X3 as predictors because I thought that they were, well, marginally interesting. And you'll notice that I have intercept, which is B0, X1, X3, and then the interaction between X1 and X3. And you'll also notice that the p-value, the critical p-value that we typically use is 0.05, and only the intercept is significantly different from 0. It's 102.5 roughly. What that means is probably not much. It just means that the mean for Y4 is not 0. So we can reject that. But excuse me, we have B's for X1 and X3, that because the standard errors are sufficiently high, the t-values are pretty low, because the estimate, these B's divided by the standard error of B, gives us our t-value, and the t-value associated with the degrees of freedom for this model are very low, or excuse me, higher p-values. The t-values are very low, and the p-values are very high, much higher than 0.05. So we failed to reject the null for X1, X3, and the interaction, which should lead us to start thinking about hypothesis testing and the potential for type 2 errors. So immediately I take a look and I see that the VIF for each one of these is almost 2. That doesn't mean that 2 is a good criterion. It just means that the variance inflation has done untoward things to our standard errors. And by doing these untoward things, what happens is it's inflated these standard errors. By inflating the standard errors, it's decreasing the probability that we reject the null. So multicollinearity is not necessarily something that we can rule out. We probably have to do something because X1 and X3 are linear, or are collinear. Next, I want to take a look at the rectilinearity of X1 to Y, and the best way to do this is with these series plots. These plots are very flexible in that they allow us to partition off the 2 primary covariates and look to see whether they are rectilinear with our dependent variable. And ideally, what we'd like to see is that we'd have a kind of a nice even line, and that would be the red dash line. But similarly, we'd like to see the green line to be right in line with the red line. The green line is just a low S, or a smooth curve, and it shows and is highly sensitive to the data. So it kind of shows that there's a little bit of disturbance, but for the most part, we can we can ascribe linearity, rectilinearity between x1 and y4 and x3 and y4. Next, I want to look at the independence of residuals, and these are the actual fitted values. These are the y-hats, and the y-hats and the residuals, if we take a look at these, we can see that there's, in general, we shouldn't see a whole lot of relationship. But we have some observations that appear to be somewhat influential. This, again, just like the green lines in the previous plot, the red line is a low S curve. It's very sensitive to the data points. And ideally, what we'd like it to be is horizontal. The independence of the residuals, the thing I'm looking for is that there's symmetry around 0, and that I could draw a distribution around this that would look pretty good. Now, speaking of distribution, we can look at the QQ norm plot, and we could then draw some inferences about normality. And you can see there's some deviations from normality on the tails, but in the center, it's looking pretty good. To the extent that this is normal or non-normal, I think in the QQ norm plot, what I generally look for is I'm looking for more of an S-shaped curve. That's where we're really going to have problems. Next, heteroscedasticity. I think that there are some influential points out here, and there's also a bit of error. The error is magnified for different levels at which we've fitted, but I'd like to see more of a plot where it has x1 and x3 as predictors of the residuals to see whether there's a difference. We can also take a look at that just in the bivariate plots. If there's heteroscedasticity, we'd expect more error to be propagated as we went up the either x1 or x3, and I'm not seeing that. Okay, next is trying to look for outliers and whether they're influential outliers, and there are a few. There's case 30 and 12 and 17 that have both leverage as well as relative importance to the parameter estimate, which is what you're getting from Cook's distance. And I would say none of them meet any threshold value, but it'd probably be wise for me to see with such a small sample size whether the results would hold true with or without those observations. Okay, so what do we have? We have non-significant results, and it may be the result of multicollinearity. We have some potential for confounded errors, some. There's a little bit of evidence for heteroscedasticity in that one figure, and I think by adding more predictors or eliminating the multicollinearity might help us explain the dependent variable better. Next, my ANOVA model, fortunately, I selected at least one significant value or predictor. Now we have a slight difference. Whereas MRC is looking at covariates, the ANOVA model is using factors, and we assume that the factors are orthogonal or independent. And that's an important part for us to get unconfounded estimates and unconfounded tests, because ANOVA doesn't really deal with multicollinearity well. MRC doesn't either. But you'll see here I have F4 and F5 predicting the same Y4 as I had before. It's just that now I've got two factors, and I've also got the interaction. So I've got different predictors, but I'm still trying to account for Y4. Okay. Don't worry about these notes. These are just notes for placeholders for me, but this is the code if you're interested in it. Here we've got F4 and F5, and the sums of squares is the sum of the squared deviations from the means. These are between group variances. That's mean squares. That's sum of squares divided by degrees of freedom is mean squares. It's another name for variance. The variance of the between factor, I take this value and I divide it by the within group factor, and I get the F value. It's a ratio of variances. That F value with 1,26 as a p-value of 0.21, non-significant at the 0.5 level, so we fail to reject the null. Think type 2 error. F5, we reject the null using the same procedure. It's this big value divided by this value. We get 5.5, and that has a p-value less than 0.5. So we've rejected the null. with F5, and F5 seems to be a good conditioning variable for us to understand Y4. So we've chopped Y4 into different classes, 2 different classes using F5. And the interaction similarly is non-significant as F4. So those are our results so far. Let's take a look at the independence of our predictors, and you can see that, well, because they're just counts, I'm looking at the design, and we don't have necessarily a balanced design, especially with a small sample size. But it's it's not a good thing, certainly, and MRC might be better because it can handle the unbalanced designs better. Next, I want to look at homogeneity of variances. Homogeneity of variances is something that's kind of critical for inferences, and you can see these cells there because it's 2 by 2. They're 4 plots, and you can see that the amount of variability around each one of these medians is somewhat disparate. There are tests for this. We can look for the homogeneity of variances, and you can see that we fail to reject the null, so therefore we can assume to a degree that the variances are equivalent. With respect to independence of residuals, you can see that the red line is pretty close to 0. That's good. Next, whoops, flew through that. Next is in terms of normality. You can see that we have some deviations from the expected value of a normal distribution. That's something we might want to take a look at with respect to those residuals. But for the most part, I'm feeling pretty confident that it's normal-ish. With respect to the fitted values and the residuals, you can see that our residuals are getting a little bit further away. And as the values increase, the y hat values increase, but not remarkably. So again, heteroscedasticity is not something that I'm terribly concerned about. And then with respect to outliers, we still have this case 30 that's causing us some problems, and we saw that with the MRC model. Okay, so what are our conclusions and implications? Well, we have a significant predictor F5, but non-significant F4 in interaction. Factors were not likely independent given an unbalanced design. Yeah, I mean, that's one of the problems and weaknesses of ANOVA. We have roughly non-equivalent variances from the plots, but it's a non-significant test, Levine's test. The residuals looked independent, a little typo there, from the predicted values of y, slight deviation from normality, a little bit of evidence of heteroscedasticity, nothing to worry about. And there's a little bit of evidence for influential observation. So MRC, again, might be a better model given the unbalanced design. Okay. And that's the first module. That's the third module, demonstration 1.